look at derivatives in the shape of a graph. So we're going to do a couple things here. We have a first derivative test. We have a second derivative test. And then we can use all of this information to try and sketch a graph of a function. So the first derivative test, this is going to help us find where the function is increasing and decreasing. So how do we find it? We need to find the critical values of the function. And that includes any discontinuities. Then we want to create a sign chart using these critical numbers. And we want to choose x values between these critical numbers to test for the sign of the derivative. If it's positive, then the function's increasing. If it's negative, then the function's decreasing. So, all right, find the open intervals for which this function is increasing and or decreasing. So, all right, we need a derivative. So that's going to be 2x squared minus 2x minus 4. I want to find the critical numbers. So I want to set that equal to 0. I think I can factor out a 2 here. So x squared minus x minus 2. And I think I can find two numbers that multiply to negative 2 and add to 1, or negative 1. So negative 2, positive 1, which actually means the critical numbers are negative 1 and 2. So I'm going to create a sign chart here and say negative 1 and 2. And I'm going to show you two ways to go about this. So the foolproof way is to test values within the interval. So let's do it. So how about to the left of negative 1 is negative 2. In between negative 1 and 2 is 0. And then to the right of 2, let's just say 3. And I'm going to plug it in to the derivative. So I'm plugging it into this function here. So what I'm looking for is just the signs. That 2 out front doesn't matter. It's positive, so it's irrelevant. It's not going to change the sign at all. So I'm just going to look at the x plus 1 and the x minus 2. Now, again, I don't care about what the numbers are. I'm just looking positive and negative. So let's see, that's going to be negative, and in the end, those multiply to be positive. So my derivative is positive, which means my function is increasing. If I plug in 0, I get 0 plus 1 and 0 minus 2. So that's positive and negative, which in the end will be negative, which means my original function is decreasing. And I can do the same thing for this last one. And we have positive and positive. So in the end, positive, which means the function's increasing. So then we can talk about the intervals of increasing and decreasing. But I also like, I call it my party trick. So method 2. I look at it as we have found the derivative, and to find the critical numbers, we were finding the zeros of the function we were given. And if you remember anything about your pre-calc and your finding zeros of really any kind of function, didn't we have something that told us the behavior of the zeros? Like if our multiplicity of the zeros was odd, then it crossed or intersected the x-axis. And if the multiplicity was even, it just touched the x-axis or was tangent to it, or I've heard it called bounced. So the zeros I have in this derivative here have a multiplicity that's odd, right? There's only one negative 1, and there's only one 2. So I know that at these critical points, they're intersecting the x-axis, which means if the left is positive, the right has to be negative because it's switching signs, because it's crossing that axis. So I can pick just one value to test. So I probably would have tested 0. So, okay, I found it was negative. So cool. negative. And I know it's going to cross at each of these, so I don't even have to test values. And I can just say plus and plus. And that would have been a lot quicker. So that's the method I'm going to use going forward. But, yeah, it's crazy. Little party trick there. All right. So then if we want a final thing, we are increasing from negative infinity to negative 1 and from 2 to infinity. And then we're decreasing in between. So from negative 1 to 2, right? Something else we can do with this first derivative test is find out those critical values if they're maximums or minimums. If there is a sign change like we just had, then it means something. So if the derivative changes from negative to positive at a critical value, then that point is a relative minimum. If we change from positive to negative, then we have a maximum. If it doesn't change at all, then it's neither. So let's do another function, and we'll do the same increasing and decreasing, but then we'll look at those critical values and find out, are they maximums or minimums or neither? So, all right, we need a derivative first. So it's going to be 4x cubed minus 16x. I want to find my critical number, so I want to set it equal to 0. And I'm going to take a GCF out. So 4x, and I'm left with x squared minus 4. I like to factor, so I'm going to take that x squared minus 4, go further, x plus 2, x minus 2. Or you could have just solved for 0. So, all right, our values, we have 0, negative 2, and positive 2. So if I go to make my sign chart here, I've got negative 2, 0, and 2. I'm going to put a star here. These multiplicities are odd, which means we cross. So I just need to test one value, and then I switch every single one. So I'm going to test, how about x equals 1? It's a nice number to work with. So I have 4 times 1 times 1 plus 2 times 1 minus 2. So that's positive, positive, and negative. So in the end, that's negative. And then I'm crossing at each one. So this has to be positive, this has to be positive, and I'm crossing here again. So that has to be negative. All right. So then we can talk about increasing, decreasing. Decreasing, decreasing, increasing, increasing. I'm going to write those. Increasing, decreasing. So we're increasing from negative 2 to 0 and from 2 to infinity. And then we're decreasing from negative infinity to negative 2 and 0 to 2. And I've seen different textbooks do different things, putting commas between them or the union symbol. Either one is all right. And then I have sign changes here. So I'm changing shape and graph. So if I'm changing from decreasing to increasing, I have a minimum. I kind of follow the shape. And if I'm changing from increasing to decreasing, I have a maximum. And then if I'm changing from decreasing to increasing, I have another minimum. So it says determine the x values of any local extrema. So maximum at x equals 0 and minimums at x equals negative 2 and positive 2. Right? Find the exact values of any relative extrema for this function on the interval 0 to 2 pi. All right, so I need a derivative. So it's going to give me 1/2 minus cosine of x. So I set that equal to 0. I get cosine of x equals 1/2. And if I think about my unit circle, right, when cosine is 1/2, we're either in this quadrant or this quadrant. And that's going to happen at pi over 3 and 5 pi over 3. So there's my critical values here, pi over 3 and 5 pi over 3. And then I want to test values here. Their multiplicity is odd, so it's going to cross every time. So I could do 0, x equals 0. So cosine would be 1. 1/2 minus 1 is negative. So all right, we keep switching here. And then I'll plug that in, 1/2 minus cosine 0. Okay, and let's just find the actual values. So pi over 3, 5 pi over 3, and we will plug these in to get the actual values. So we're decreasing, increasing, decreasing. So we're changing from decreasing to increasing. So there's a minimum at pi over 3, and then there is a maximum at 5 pi over 3. And now I'll just find those actual values. So I'll just go up here. So g of pi over 3 is going to be pi over 6 minus, and sine of pi over 3 is root 3 over 2. Let's just leave it. I'll just leave it in the exact. I don't care about the decimal. And then 5 pi over 3. Let's see, if I do 1/2, it's going to be 5 pi over 6. And then the sine of 5 pi over 3 is negative root 3 over 2, so really that will be plus. Alrighty. And there's our points. Alright, so another thing to look at is we got to be careful when answering questions. We got to look for some keywords. So are we looking for the actual extrema values, which would be y values, or the location of the values? So if we're looking for the extrema, we're looking for keywords like what. And for location, we're looking for keywords like where. Right? So find the relative extrema for this function. So that's the y value. So, all right, let's find the derivative. So we get 2/3 x squared minus 4 to the negative 1/3 times 2x, which I will make that a 4x over 3, and then cubed root of x squared minus 4. When I set this equal to 0 to find any extrema, my critical values, I need to find the zeros and where we're undefined. So that's setting the numerator and denominator equal to 0. So one critical value is 0. It has a multiplicity that is odd, so it's going to cross on either side. And then we're going to look at this as well. So I can divide both sides by 3 and then cube both sides, and I'll be left with x squared minus 4 is still 0. So x is going to be plus and minus 2. Now, because it creates a 0 in the denominator, it's going to create a vertical asymptote. And we can say that for vertical asymptotes, the behavior of them, if their multiplicity is odd, then on either side, it'll be going opposite directions. So it might look like this and this. And if the multiplicity is even, they go the same direction. So it would look something like this. Okay. So I can still use the same party trick here. Multiplicities are all odd, so they will cross at every point. So maybe I want to use x equals 1 because that's a nice number to work with. So 4 times 1 is positive. And then let's see, 3 is going to be positive. If I plug in 1 squared is 1. 1 minus 4 is negative 3. Cubed root of a negative number is going to be a negative number. So in the end, this is negative. And then I know it's going to switch. And switch at each one. And I can do a quick double check. So, all right, let's do something like 5. So positive in the top. 5 squared is 25 minus 4 is positive. Everything is positive. Okay. So we want to find the extrema. So if my derivative is negative, I'm decreasing. And if the derivative is positive, I'm increasing. That creates a minimum at -2, a maximum at 0, and then another minimum at 2. Now it just says find the extrema. I'd go ahead and find the whole ordered pair, but it's really asking for the y values. So I can plug these into the original equation, or the original function. So -2 squared would be 4. 4 minus 4 is 0. 0 to the 2/3 is 0. And then very similarly, 2 squared is 4. 4 minus 4 is 0. 0 to the 2/3 is 0. And then if I plug in 0, I get -4 to the 2/3. So -4 squared is what, 16? So the cube root is 16. All right. And so there are my extrema values. Really, I could just use the y's. Find the x-coordinates of the relative extrema for this function. Okay, so I could do a product rule, or I could multiply these things out. So I really have x to the 2/3 times x minus 2. So I would make that an x to the, let's see, that could be 3/3. I add the exponents, and then I don't have anything to combine there. Then I could do a derivative. Oh, this is h of x this time. So 5/3 x to the 2/3. And then minus 4/3 x to the -1/3. All right, let's set that equal to 0 and solve. I'm going to move over here to do that. So I have 0 equals 5/3 x to the 2/3 minus 4/3, and I'm going to drop that to the bottom. So I'll add this over. And then I'll probably cross multiply. So 4 times 3 is 12. 3 times 5 is 15. And x to the 1/3 times x to the 2/3, I can add that together, right? And then divide both sides by 15. And reduce that fraction. So both go by 3. So 4/5. And then, okay, multiplicity is odd there. So it's going to cross on either side. And honestly, that is reason enough to be done. We just want the x-coordinates of the relative extrema. So there we have it, because we know it's going to cross. So we know there's going to be a sign change, but we can keep going anyway. Let's plug in x equals 0. Let's not do that, because if I go into the derivative, that will make a 0 in the denominator. which means that's another critical value here. Because we want also where the derivative is undefined. All right, so it means there's an asymptote there. But still, it crosses because that multiplicity is odd. Okay. Or not crosses, it goes opposite directions. So if one's positive, the other's negative. All right, so how about using 1? I'll go to the derivative here. So we've got 5 thirds and then minus 4 thirds, right? Which will be 1/3, so that's positive, which means we'll switch. So we can say, all right, we have a maximum at x equals 0 and a minimum at x equals 4/5. And there we have it. All right, given g of x, find the intervals of increasing and decreasing and the x coordinates of the relative extrema. Okay. So to find a derivative, we gotta do quotient rule. So low d high minus high d low all over low low. And then we'll clean it up. So it's going to give me 3x cubed minus 6x squared minus x cubed plus 3 all over x minus 2 squared. I think I can combine more like terms. So 2x cubed minus 6x squared plus 3. All right, so I want to set that equal to 0 and find the zeros and where we're undefined. So we're undefined at x equals 2. And that multiplicity is even, so it'll be going in the same direction. So it's either going to be both positive or both negative. And then we'll do that numerator, 2x cubed minus 6x squared plus 3. Set that equal to 0. And for sake of time, because I haven't even got to the second derivative test, and I'm at 23 minutes in this video, I'm going to use a graphing utility and find the zeros that way. Oh, these are big. Decimals here. And by big decimals, these are giving me big fractions as well. So I'm going to round. And I get negative 0.64, 0.8315, and 2.81. So I'll put these on here. The multiplicities are all odd, so they're going to cross each time. So let's just pick one value, and I'm going to say x equals 1. Nice number to work with. So, that denominator is always going to be positive because it's of the quantity squared. And then let's see, 2 minus 6 is -4. -4 plus 3 is -1. So negative, positive, negative, positive, negative. Because we're going to switch everywhere. Oh, except for at 2. Because I had a multiplicity that was even. So actually I switched that there. Okay, so we're increasing from negative 0.64 to 0.83 and 2.81 to infinity. And then we are decreasing from negative infinity to negative 0.64, from 0.83 to 2, and 2 to 2.81. And then the x-coordinates of any relative extrema, I'll just highlight those. I have a sign change, I have a sign change. I don't have a sign change, so that's not an x value of an extrema. And then I do have another sign change, right? All right, we're going to go to the second derivative in the second derivative test. So the first derivative tells us whether we are increasing or decreasing. The second derivative is going to tell us the concavity. So whether we're concave up or concave down. I also like that I'm looking ahead, and that should say concave, not convex. That's crazy. Okay, with first derivatives. Oh, I just said all that. So our critical, we still want to find critical values, the zeros and where we're undefined in that second derivative. If we have a sign change in that second derivative, we call those points of inflection, because that's where we are changing concavity, right? And then here's just some facts to know. So if we're concave up, then our first derivative is increasing. If we're concave down, then our first derivative is decreasing. And then if our second derivative is positive, the graph of the function is concave up. And if the second derivative is negative, then the graph is concave down. Okay. So we have this function here, determine where we're concave up and concave down, and if there's any inflection points. So I need a second derivative. So I've got to find the first one. So it's going to give me x squared minus 1. And then a second derivative is just going to give me 2x. So if I set that equal to 0, then x is 0, right? So second derivative. And then we'll see what the original function looks like. So we do cross here, right? Multiplicity is odd. And so, I don't know, let's use x equals 1. Well, 1 times 2 is 2, so it's positive, which means the left is negative. So the original function, we're concave down and concave up. We have that sign change. So point of inflection at x equals 0. We could find the actual ordered pair by plugging it back into the original f of 0. And that's going to give me 0. So we have a point of inflection at 0, 0. And then we are concave up from negative infinity to 0. And concave... Oh, I have that backwards. We're concave up from 0 to infinity and concave down from negative infinity to 0. Right? So let's find some inflection points. So determine any inflection points and discuss the concavity of this graph. So let's find a first derivative so I can find a second. So 4x cubed minus 12x squared. And 12x squared minus 24x. If I set that equal to 0, I want to find a GCF here. So 12x, and I'm left with x minus 2. So my critical points are 0 and 2. We're going to cross each time because that multiplicity is odd. And then 1, again, is always really nice to work with. So 12 times 1 is positive, and 1 minus 2 is negative. So in the end, it's negative. right? So that's our second derivative. So our original, up, down, up. So we have points of inflection at 0 and 2, and I'll get those values. If I plug in 0, I get 0, 0 into the original function. If I plug in 2, I get what? 2 to the 4th minus 4 times 2 cubed, which is 8. So which means 2 to the 4 is what, 16? And then minus 32, so negative 16. And then we're concave up from negative infinity to 0 and 2 to infinity, and concave down from 0 to 2. Right. Find inflection points and the intervals of concavity. All right, I'm giving you easy functions here. So 15x squared plus 4x minus 3. And then a second derivative, 30x plus 4. So if I set that equal to 0, so you had to subtract 4, divide by 30, and reduce that fraction. So negative 2/15. So negative 2/15. Let's plug in 0. Plug in 0, I get positive. Oh. As I plugged in, I could plug in negative 1. Yeah, I'd get negative. All right, so we're concave up from negative 2/15 to infinity, and down from negative infinity to negative 2/15. And then points of inflection, because I don't want to deal with a fraction, we'll just say point of inflection at x equals negative 2/15. All right, so using the second derivative to find the extrema. So if x equals c is a critical number of the function, then f prime of c equals 0, or f prime of c doesn't exist. So this makes that x equals c a possible maximum or minimum. We're just testing the values. So if the second derivative is positive, that means the original function is concave up, right? So it means there's a minimum. And if it's concave up, the original, or the first derivative, is increasing. For negative, we're concave down, which means there's a maximum. And the first derivative is decreasing. And then if it's neither positive or negative, which seems a little strange, so it being neither positive or negative just means it's equal to 0. Then we would have to use the first derivative test to further analyze it. So there's a possible point of inflection, which means there's a possible relative max or min. But we'd have to use that first derivative test to be sure. All right, so use the second derivative test to find the extrema for this function. So, all right, let's find the second derivative. Set it equal to 0, and I'll find a GCF here. So I'll get 0 and 4. Let's plug in 1. So 12 times 1 is positive. 1 minus 4 is negative. So in the end, that's negative. And these multiplicities are odd, so it will cross. And we want to find the relative extrema here. So I'm going to plug in these values now. So if I plug in 0 into the original function, I get negative 5. If I plug it into the second derivative, I get 0. So I would need to use the first derivative and plug it in to see what happens. But we're just using the second derivative, so we'll just say can't be determined with the second derivative. And oh my goodness, these numbers are not right here, because I want the critical numbers of the first derivative, and I'm just substituting it in to the second derivative. So I need to go back to that first derivative. So I get 0 and 6. And then I'm going to plug this into the second derivative. So if I plug in 0, I get 0, which still can't be determined with that second derivative. Then if I do second derivative at 6, I get probably a really big number. 12 times 36, and then minus 48 times 6, I get 144. So it's positive, which means it's concave up, which means there is a minimum at x equals 6. And I can plug that into the original function and see what that gives. So 6 to the 4th minus 8 times 6 cubed, and then minus 5, I get negative 437. All right. Okay. So if I just want to summarize all this behavior here. So what's really happening? If my first derivative is positive and my second derivative is also positive, then we are increasing and concave up. First derivative being positive, second derivative being negative means we're increasing, but concave down. And then if the first derivative is positive and the second derivative is 0, then we're increasing and there's a point of inflection. All right, if the first derivative is negative, the only thing that changes from that first column is instead of increasing, we are decreasing. So decreasing and concave up. Decreasing and concave down. And decreasing and point of inflection. All right, so what if we have a critical point in the first derivative and what's happening on the second derivative? So we have a critical point, and the first second derivative is positive, we have a relative minimum and we're concave up. If the second derivative is negative, we have a relative maximum and we're concave down. But if the second derivative is 0, then the function is smooth or level, and there's a possible inflection point. Right? So let's see if we can kind of tie all this stuff together to try and draw some graphs. So the curve sketching piece of this. So, all right, if our first derivative is positive and the second derivative is also positive, we know we're increasing and concave up. So we could look something like this, increasing and concave up. If the first derivative is negative and the second derivative is positive, we are decreasing and concave up. So that's going to be the other part of the parabola. I always think parabola. All right, and then first derivative is positive, but second derivative is negative. We're increasing, but concave down. And then we're decreasing and concave down. Right? Now let's see if I can sketch a graph given some conditions. So, okay, we have first derivative is positive. I'm going to draw some things out. So, first derivative looks like we have -1 and 3 as values here. So, we are positive from -infinity to -1 and from 3 to infinity, and negative from -1 to 3. So that means my original, we are increasing, decreasing, and increasing again. And then second derivative looks like we have values -3, -1, and 3. So we are positive and positive, and then negative and negative, which means concave up, down, up, down. The limit as x goes to -infinity for the function is -4, and the limit as we go to positive infinity is 4, +4. Okay, so eventually, as we go to infinity, we're eventually hitting 4. 1, 2, 3, 4. So eventually, and then as we go to negative infinity, we're eventually hitting -4. I have a maximum at -1 and a minimum at 3. So let's just make some values. And then the second derivative, I have some points of inflection at -3. -1 and 3. Okay. But I'm increasing from -infinity to -1. So I'm going to kind of do a little rough sketch here. Right? Increasing. I'm changing concavity, so that concave up and then concave down. This is going to be a maximum, so I've got just my dotted line here. And then I'm decreasing from 1 to 3, -1 to 3. So I think I can follow that pattern down, maybe. And then at 3, I'm changing concavity, and then we turn to increasing. And I think that follows all the conditions. So I'll just go ahead and make it more solid. And there we have a sketch that meets all those conditions. All right, so it's not going to be perfect, and there's probably many other ways you can make a graph that meets these conditions, but that was what met it for me. All right. Goodness, I have so much more left, and I'm like 45 minutes into this. Okay. So here we have a graph, and we're looking from -8 to 8. On what open intervals is the function increasing and concave up? All right, so we're assuming this is f of x. So increasing and concave up. It's going to be here and here, which would be -5 to -2 and 4 to 6. All right, what are we decreasing and concave down? Decreasing and concave down. So -1 to 2. What x values do we have inflection points? This is where we are changing the concavity. So concave up, and then it switches, so -2. And then we're concave down, then it switches again, and then concave up until we switch again. So there's 3 points there. All right, we're going to assume this graph is now the derivative. So where are we decreasing? So that is when the derivative is negative. So that's going to be from 2 to 6. Where do we have a local minimum? This is where the first derivative is going to change from negative to positive. Oh, I said maximum, or I said minimum, but that says maximum. So I actually need to switch that. So this increasing to decreasing. So positive to negative. So that's going to happen right there at 2. Function, or the derivative, sorry, is changing from positive to negative. Then it's asking what intervals is the function concave down. So this is where the derivative is decreasing. So we are decreasing here, here. So that's going to be from what? -8, not infinity, to -5. And -1 to, oh my gosh, we're still decreasing there. So -1 to 4. And then at what values does the function have an inflection point? So this would be where the second derivative is 0 and changes sign. So I have zeros here, here, and here. Second derivative is 0. So that is where we have slopes of 0, which is here, here, and here. And then are we changing signs? So increasing to decreasing yeah, all of them are changing signs because we're changing from increasing to decreasing. So x equals -5, -1, and 4. All right, so now we're going to pretend that this graph is the second derivative. So where we concave down. So that is where the second derivative is negative. So that's going to be from 2 to 6. And then what values of x do we have in inflection point? So this is where the second derivative is equal to 0 and changes sign. So we're changing here and here. This would be equal to 0, but it doesn't change sign. So we have inflection points at 2 and 6. All right, so let's try and analyze a function. See if we can try and draw one. And I think this is, oh, I was going to say the last one, but I got 2 more here. Okay, so we want to figure out what our domain of our function is. We can probably find the x and y intercepts or any asymptotes and symmetry. Then we want to find critical points and find where we're increasing and decreasing. And then find any local maximums or minimums. And then find the concavity and points of inflection. And then try and draw a picture. So I have a function here. Just based off of some pre-calc knowledge here, if I were to multiply this out, I have x and then x squared. So it's some form of x cubed. So I'm going to look something like this. So potentially I have maximums and minimums. And let's just step through it. So find any x and y intercepts. So the x intercepts are the zeros of the graph. And it's already factored for us. So we have x-intercepts at -2, 0, and at 1, 0. And we cross here and touch here. Y-intercept is when the function is is 0. X is 0. So that's going to give me 2, and then -1 squared, which is just going to be 0, 2. Find the first and second derivatives, and then we'll do sign chart stuff. So the first derivative, why not do product rule? So left d right plus right d left. Then I'll multiply things out. So that's 2x minus 1. So it'll give me 2x squared minus x plus 4x minus 2. And then x minus 1 squared is x squared minus 2x plus 1. I'll combine some like terms. So 3x squared minus 3x. Oh, that'll be 3x and minus 2, so plus x, and then minus 1. So then a second derivative is going to be oh my gosh, I'm struggling today. That should be a 2. So then when I multiply here, that changes everything right here. So it's 2x squared minus 2x plus 4x minus 4. So then let's combine my like terms. So we have 3x squared. The x's will cancel out, and then minus 3. So the second derivative is going to be 6x. So if we do critical values here, for the second derivative, we would have x equals 0. And then for this one, we'd have, let's see, add 3, divide by 3, so it'd be 1. And the square root of 1 would be positive and negative 1. All right, so let's find our stuff. So we have negative 1 and 1. And let's plug in. So if I do 0 into the first derivative, I get negative. So there's my increasing and decreasing. And then let's do, second derivatives down here. Okay, determine any relative extrema. So we do have some sign changes. So let's see, we have a maximum at -1 and a minimum at 1. If I go back into the original, let's see, -1 plus 2 is -1. And then that is going to be -2 squared. So 4, -4. Oh my gosh, that is not -1, that's +1. Which means that'll be +4. And then we can plug in 1, so that's going to be 3. And then times 0, so 0. All right, second derivative, that critical value was 0. And then we can look at, if we do negative, we have negative number times 6, so negative, and then positive, which means concave down, concave up, which means we have a point of inflection at 0. If I plug that in, we've already done that in the first part. If I plug in 0, I get 2. So let's see. Oh, points of inflection, 0, 2. And let's see if we can draw a graph. So let's find all the points we have. We know we have x-intercepts at -2, 0. What was the other one? 1, 0. We know we have a y-intercept of 0, 2, and a point of inflection there. We have a relative maximum at -1, 4. And a minimum at 1, 0. So remember, this is a cubic function, so potentially it'll look something like this, right? So I think I have all I need, right? Looks something like that. All right. Let's see if we can kind of do the same for this last one here. So let's find some first and second derivatives. Actually, you know what? No, this video is almost an hour long. So how about this is practice for you? All right. If you have any questions, let me know.